the trig equation. If you're still unsure of how to use that, we will be using it in this video, so hopefully you'll get a better understanding. So the topics that we're going to cover in this video is 1. Solving quadratic trigonometric equations. Then we'll move on to how to use trig identities to solve trig equations. If you're not entirely sure what a trig identity is, there is another video that explains that, so you should definitely watch that before you watch this. If you already know what a trig identity is, I hope that you will continue watching. After we cover that topic, we'll move on to the combination of squaring equations and then using trig identities. And finally, in the last part, we will go over how to approach a more advanced problem, and hopefully you'll be able to approach any trig equations after this video. So quadratic trigonometric equations. Well, in your previous pre-calculus sequence, you might have gone through what a quadratic equation really is. Usually it's in the form of ax squared plus bx plus c. Okay, so let's look at an example of 2x squared minus 9x is equal to 5. Now, when you approach a quadratic equation, you're usually told to move all the terms to one side, and so you have 0 on the other. So we get 2x squared minus 9x minus 5 is equal to 0. Now, after you get that, you would usually factor it out. So in this case, we would get 2x plus 1 times x minus 5 is equal to 0. And then we would set the factors to 0. So we get 2x plus 1 is equal to 0, and x minus 5 is equal to 0, and we would solve for x, which in this case we get negative 1/2, and x is equal to 5. Now, let's look at a trig equation. Let's find the general solution for 2 sine squared x minus 9x is equal to 5. Now, to approach these kinds of trig equations that look kind of like a quadratic equation, there are 2 kinds of methods. The first method is we treat sine x simply as a regular variable. Now, when you were doing 2x squared minus 9x minus 5, you dealt just with the x. We take the similar approach when we do trig equations, but we just treat sine x as if it was an x. So in this case, we would factor it out to 2 sine x plus 1 times sine x minus 5, just like we did 2x squared minus 9x minus 5 and factored it to 2x plus 1 times x minus 5. And then we would set the 2 sine x plus 1 to 0 and sine x minus 5 to 0. And then we get sine x is equal to negative 1/2 and sine x is equal to 5. Now when you just dealt with x, once you got that, you were done. You got x is equal to negative 1/2 and x is equal to 5. But in this case, we're using sine x, so we have to do an extra step. So the extra step involves finding the x values that make sine x equal to negative 1/2. Sine x is never equal to 5. The range of a sine graph goes from -1 to 1. There is no 5 within the range of a sine graph, so we can ignore sine x is equal to 5 and just focus on finding the x values that make sine x equal to negative 1/2. So if we look at the unit circle, we have to find the x values that make sine x equal to negative 1/2, and when we look on an interval of 0 to 2 pi, remember from 0 to 2 pi means like one full rotation of the circle, we find that when x is equal to 7 pi over 6, and when x is equal to negative pi over 6, or we can also say 11 pi over 6, sine of x is equal to negative 1/2. Remember, when we say 7 pi over 6, we're going from 0 and then we go counterclockwise. I put x is equal to negative pi over 6 because that's going counterclockwise, but if that's a bit confusing for you and you just want to stick to going counterclockwise, you could write the negative pi over 6 as 11 pi over 6, so then you'll just have x is equal to 7 pi over 6 and x is equal to negative pi over 6. Now this question is looking for a general solution. So x is equal to 7 pi over 6 and x is equal to negative pi over 6 is right, but that doesn't encompass all of the solutions that make this equation true. So because we want to acknowledge all of the x values that make sine x equal to negative half, right? So we have to acknowledge that it goes around and round. If 7 pi over 6 goes one rotation, so it goes plus 2 pi, and it goes to 19 pi over 6, that's still going to give us sine x is equal to negative 1/2. So we have to do x is equal to 7 pi over 6 plus 2k pi, but we also have to include x is equal to negative pi over 6 plus 2k pi, where k is an integer. Now let's look at the second method. The second method, we let sine x equal to y. If dealing with sine x is a bit confusing, you can always use this approach. And instead of doing 2 sine squared x minus 9 sine x minus 5 equal to 0, you would put 2y squared minus 9y minus 5 is equal to 0. And then you would do the same thing. You would factor it out in terms of y, so you'll get 2y plus 1 times y minus 5 is equal to 0. And then you set the equations equal to 0. You solve for y, but you have to remember that y is equal to sine of x. So you have to get sine x is equal to negative half, sine x is equal to 5, and you'll get the same answer of x is equal to 7 pi over 6 plus 2k pi, and x is equal to negative pi over 6 plus 2k pi. Now, let's move on to how to use trig identities. Let's try to solve the equation 1 plus sine x is equal to 2 cosine squared x on the interval 0 to 2 pi. Now, we have cosine squared x, so you might be inclined to think, okay, now we can use a quadratic approach. But the problem is that we have sine x, so unfortunately, we can't. Then what can we do? Well, when you were learning trig identities, perhaps the first identity that you learned was the Pythagorean theory, or the Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. Now, how can we utilize this identity to solve this equation? Well, if you notice in the equation, we have cosine squared x. So if we rearrange the Pythagorean identity, we can get 1 minus sine squared x is equal to cosine squared x. So we isolate the cosine squared x. Now, if we put this into our equation, we'll get 1 plus sine x is equal to 2 times 1 minus sine squared x. Now, if we multiply the 2 out, we get 1 plus sine x is equal to 2 minus 2 sine squared x. Now this kind of looks like a quadratic equation. So we move all the variables to one side, and we get 2 sine squared x plus sine x minus 1 is equal to 0. We factor it out. 2 sine x minus 1 times sine x plus 1 is equal to 0. Set the factors equal to 0. And then we solve for sine x. Sine x is equal to 1/2, and sine x is equal to negative 1. So now we have to look for when sine of x is equal to 1/2. Well, if we look at the unit circle, we see that sine of x is equal to 1/2 when x is equal to pi over 6 and when x is equal to 5 pi over 6. Now this time we are on a restricted interval from 0 to 2 pi. So we don't need a plus 2 pi k to acknowledge all the values. Because it's from 0 to 2 pi, the x values pi over 6 and 5 pi over 6 make sine x is equal to 1/2, but only on the interval 0 to 2 pi. Now let's solve for when x is equal to, sine of x is equal to negative 1. Well, if we look at the unit circle, when x is equal to 3 pi over 2, sine x is equal to negative 1. Again, we're on a restricted interval from 0 to 2 pi, so there is no need for the k. So we can just say that x is equal to 3 pi over 2. Now let's look at another type of trig identity question. Let's try to solve the equation sine 2x minus cosine x is equal to 0 on the interval 0 to 11 pi over 4. Remember, whenever you see the question asking on the interval or on a specific layout, when they don't say, look for the general solution or what are all the values of x that make this statement true, you want to remember that you are on a restricted specific interval. In this case, we have 0 to 11 pi over 4. Now, when we look at this question, we have sine 2x minus cosine x is equal to 0. Well, first of all, there's no squared, so we can't use the quadratic approach. And we can't factor anything out either. because we also have 2x and x. So that's a bit problematic. But if you remember the double angle formula, sine 2x is equal to 2 sine x cosine x. Now, first you might be a little bit hesitant to use this because, in the previous example I said you want to try to make all of the values of the equation the same. So if you have it in terms of sine, you want to have all the terms in terms of sine. If you have other functions, then it might complicate things. And so you might be a bit hesitant to use this double angle formula. But if you replace sine 2x with 2 sine x cosine x, then you get 2 sine x cosine x minus cosine x is equal to 0. So now both two terms have cosine x. If you factor out the cosine x, you get cosine x times 2 sine x minus 1 is equal to 0. You set the cosine x equal to 0, 2 sine x minus 1 is equal to 0, and you get cosine x is equal to 0, sine x is equal to 1/2. Now let's look for the values of x that make cosine x equal to 0. Again, we look at the unit circle and we find that at x is equal to pi over 2 and when x is equal to 3 pi over 2, cosine x is equal to 0. But this is only on the interval 0 to 2 pi. The question is asking us to find the x values on a restricted interval of 0 to 11 pi over 4. So it goes from 0 to 11 pi over 4. So if we go on this interval, we get 3 values of x that make cosine x equal to 0. Pi over 2, 3 pi over 2, and 5 pi over 2. You might be tempted to say that 7 pi over 2 also is equal to cosine x equal to 0. That is true, but we're on an interval of 11 pi over 4. 7 pi over 2 is not on the interval of 11 pi over 4, so we do not include that in our solution. Next, we have to find the values of x that make sine x equal to 1/2. We look at the unit circle, we find that at x is equal to pi over 6 and x is equal to 5 pi over 6, sine x is equal to 1/2. Now again, we are on a restricted interval from 0 to 11 pi over 4. So we find that 3 times the x values would give us sine x is equal to 1/2. When x is equal to pi over 6, when x is equal to 5 pi over 6, and when x is equal to 13 pi over 6. Again, we do not say that 17 pi over 6 is a value of x that makes sine x equal to 1/2. That is true. 17 pi over 6 in sine does make it 1/2, but our interval is from 0 to 11 pi over 4. 17 pi over 6 exceeds this interval, so we do not include this in our solution. Okay, now let's move on to how to use squaring and using identity to solve our trig equations. Let's find the general solution for cosine x plus 1 is equal to sine x. Again, this is general solution, so whenever you see general solution or all x values, you want to think, okay, I have to use plus 2k pi to acknowledge all of the values of x. So when we first look at this equation, there seems to be really no approach. There's no squared, so we can't use a quadratic equation. And we can't seem to use a double angle formula either. But the thing is that let's try squaring both sides of the equation. So let's square cosine x plus 1, and let's square sine x. When we square both sides of the equation, we get cosine squared x plus 2 cosine x plus 1 is equal to sine squared x. Remember, when you square cosine x plus 1, it's not cosine squared x plus 1. You have to multiply out each term so that you get cosine squared x plus 2 cosine x plus 1. Don't make that mistake. I've made it many times on the test and it always brought my grade down. So try to avoid that as much as possible. Now we look at this equation and we have sine x and we also have cosine x. And if you notice, we have a sine squared x. If we want to make all the terms in terms of cosine, we can use the Pythagorean identity by rearranging it and replacing sine squared x with 1 minus cosine squared x. Now we move all the terms to one side and we get 2 cosine squared x plus 2 cosine x is equal to 0. Then we factor out the cosine and the 2, so we get 2 cosine x times cosine x plus 1 is equal to 0. we set cosine x equal to 0 and 2 cosine x plus 1 equal to 0. And now we have to find where cosine x is equal to 0. So we look at the unit circle, and we find that from pi over 2 and at 3 pi over 2, cosine x is equal to 0. Now this question was asking us for the general solution. So we have to use k. So our solution here would be x is equal to pi over 2 plus 2k pi, or x is equal to 3 pi over 2 plus 2k pi. Now we have to find the values of x where cosine is equal to negative 1/2. Remember, we got this negative 1/2 because we said that 2 cosine x is equal to negative 1. So we just divided 2 cosine x by 2, and we divided negative 1 by 2. So if we look at the unit circle, we find that when x is equal to 2 pi over 3 and when x is equal to 4 pi over 3, cosine x is equal to negative 1/2. Again, we're looking for the general solution, so just writing out x is equal to 2 pi over 3 and x is equal to 4 pi over 3 does not encompass all of the solutions. So we have to write x is equal to 2 pi over 3 plus 2k pi, or x is equal to 4 pi over 3 plus 2k pi. Okay, so now we've covered the majority of different techniques that you can use to solve trigonometric equations. Let's take a look at a more advanced trigonometric equation. Given the equation 4 tan cube x plus 8 tan squared x plus 2 is equal to 3 tan x plus 8, find all solutions of x. Okay, so at first glance this kind of looks a bit daunting. You have many terms and you have a cubed and a squared. But let's try to move all the terms to one side and see if we can factor out anything. We move it to the left-hand side. We get 4 tan cube x plus 8 tan squared x minus 3 tan x minus 8 plus 2 is equal to 0. We simplify it and we get 4 tan cube x plus 8 tan squared x minus 3 tan x minus 6 is equal to 0. Now if you notice, there are 4 terms. In your pre-calculus sequence, you might have learned about if you have 4 terms, you want to see if you can factor out anything by dividing the 4 terms into like different categories. Like you treat 4 tan cube x plus 8 tan squared x together, and then you look at negative 3 tan x minus 6 together. So if we look at the first 2 terms, we see that they have a common factor of 4 tan squared x. So if we factor that out, we'll get tan x plus 2. If we look at the negative 3 tan x minus 6, if we factor out negative 3, we get negative 3 times tan x plus 2. Both of the parts have a tan x, so we factor tan x plus 2. Sorry, I was meant to say tan x plus 2. So then we get 4 tan squared x minus 3 times tan x plus 2 is equal to 0. Again, we equate the factors to 0. So 4 tan squared x minus 3 is equal to 0, and tan x plus 2 is equal to 0, and we try to solve for tan x. Now when you have 4 tan squared x minus 3 is equal to 0, you have to remember that there's a squared. So you have to factor again. When we factor this again, we get 2 tan x minus root 3 times 2 tan x plus root 3 is equal to 0. And then we set them equal to 0, and we get tan x is equal to root 3 over 2, tan x is equal to negative root 3 over 2, and tan x is equal to negative 2. Okay, so unfortunately the values don't come out so nicely. If we take the inverse of tan x of root 3 over 2, we get that it roughly 0.714 radians, or 40.9 degrees. Now, you have to remember that the inverse of tangent, it gives us a range of negative pi to 2 to pi over 2. So on the unit circle, it only covers the red arc. It doesn't cover the values on the other side. This is problematic because if you just say that when x is equal to roughly 0.714, well, when x is equal to 0.714, it makes tan x equal to root 3 over 2. You're technically correct, but you're not acknowledging all of the x values that make tan x equal to root 3 over 2. So you have to plus pi to your original value that you get when you use your calculator and find the inverse of root 3 over 2. If you do that, you do 0.714 plus pi, which is roughly 3.86 radians or 220 degrees. Now if you look at the unit circle, it appears in the first quadrant and in the third quadrant. So as a result, your solution is x is equal to 0.714 plus 2k pi, or x is equal to 3.86 plus 2k pi. Now let's look at the x values that make tangent x equal to negative root 3 over 2. If we take the inverse of negative root 3 over 2, we get negative 0.714 radians, or negative 40.9 degrees. Again, the inverse of tangent only gives us gives us values that range from negative pi over 2 to pi over 2. So on the unit circle, it's only this part that is marked by the red marker. And so, to acknowledge all of the x values, we have to plus negative 0.714 to pi, and we get 2.43 radians, which is roughly 139.1 degrees. But because we're looking for all of the values of x, we have to say x is equal to negative 0.714 plus 2k pi, or x is equal to 2.43 plus 2k pi. And now lastly, we have to find the x values that make tangent x equal to negative 2. We take the inverse and we get negative 1.107 radians, or negative 63.4 degrees. Again, we have a restricted range from inverse tangent that goes from this part of the unit circle. So we have to plus pi to negative 1.107, and we get 2.03 radians, which is roughly 116.56 degrees. And thus our solution is x is either negative 1.107 plus 2k pi, or x is equal to 2.03 plus 2k pi. That is the end to this video. I hope that it was of some help to you, and I hope that your studying for this topic goes successfully and smoothly.